now I'm going to show you an example using tools provided by Prover technology. It's a Sudoku example. I didn't choose the example from the railway, which we are we have been working on a lot, because we want to present with a very generic the problem that probably most people are familiar with, instead of a very domain-specific problem. So in Prover, we have done formal verification by model checker. So we have a model checker called PSL, which is the state-of-art proof engine for industrial applications, which has been used for many really big, complex railway signaling system, for example, interlocking and CBTC. And we have a language called HLL. It's a formal language for modeling discrete time sequential behavior and expressing properties of those behaviors. So it started with the Boolean logic and integer arithmetic, but now as time goes, has been continuously evolving, and now we support like enums, arrays, tuples, structures, recursive functions and qualifiers, and more. So it becomes very much more expressive. You can model and express more systems. Okay, so I'm switching to this example. So this is a Sudoku puzzle that I have written in HLL. By the way, if you want to see the blog about this Sudoku problem modeled in HLL, you can go to this link. There's a blog about it. But now I just show you. I won't bother you with the technical details, but trying to explain it as. So we have, assuming that everyone knows about Sudoku problem. This is 9 times 9 metric with numbers in each slot. There's initial. This is the puzzle itself is presented using this 2-dimensional array called partial grid as numbers, but there are lots of places there are 0, which present empty slots that you need to fill them with the right numbers in order to solve this puzzle. And this is an example from the website called 7 Sudoku. It's labeled as a very difficult category. So we have a declaration and called a grade. It's also a 2-dimensional array of 9 times. So supposedly we need to fill in this array in order to, you find a solution and you fill up with your solution in this array. Okay, so because HL is a declarative language, so here we use a Boolean variable to describe what it means to be a solution to a Sudoku problems. We say that we have quantifier or. So for each number from 1 to 9, we are saying, okay, for all rows in this matrix, there exists a column where this digit or this number can be found at. Okay, I hope you understand it. This is the first this is the declarative manner to describe the solution. And the second one here, for all columns, for each column there exists a place where you can find this digit at. Okay, and for each matrix, because the this 9 times 9 matrix that consists of 9 3 times 3 submatrix. So in each such submatrix, you can find a slot in it where this digit can be found. Okay, I hope you understand this objective. So, and before I actually run it for verification, actually this model checker, the PSL, can be used to find the solution for it, because this is the objective. And now we are not proving this is there. We claim by adding a negative here, negation here, we ask the model checker to the proof engine to prove there's no objective, there's no solution to this problem, but actually there is. So this is the way to actually to solve the problem. So I'm running this Sudoku. So we're using induction, and we want to use Y to be able to present this the context example. So now actually the proof engine enters this interactive environment where you can actually show the counter model, because we are expecting the counter example. So we are setting these steps to 9. So this is the rows. Okay. So this rows, this array, is actually an array of streams, because there's so many details I probably won't have time to cover. But now you can say that the array is basically a transformation of the grid we have been talking about, but only for better in presentation of the counter example. So you can see here, actually, you can see this matrix here with in every place this is a number. There is a number, and so now you get a solution. Okay. So we know that we can actually find a solution to this problem, but we want to prove some invariant of this Sudoku problem in general, because we didn't really have to check if it's a right solution anyway, but we can actually use the proof engine to define some properties. You can think of them as safety requirements, because what we do here is we try to describe the invariant of the Sudoku problem. So what a solution to a Sudoku puzzle must satisfy. It's sounds similar to the syntologin problem we have just described. So I just quickly go through them. So now we claim that any number from 1 to 9 can only occur 9 times in this big 9 times 9 matrix. I think it is a valid property. And now for each row of this 9 times 9 matrix, there's a uniqueness you have to guarantee, right? I mean, this is the basic point. This is the point of Sudoku puzzle. Okay, so I won't go through the details of this formalization, but basically I still know. Okay, for each row of this matrix, and if you look at a row of this matrix, and there's no 2 places that hold the same number. Okay, this column A and column B. If they're not equal, then this grid. Then there's you cannot replicate numbers in 2 different places. Okay, and then you put this proper and the prop 2 in this place called the proof obligation, where you basically this is where you put the properties you want to prove. And then we run this PSL. which proves check model checker to prove it. Okay, boom, you see it's valid, and those two POs are valid. Okay, I hope you understand what I just said. But as I said, for the Sudoku problems, if you are interested, you can go to the this link.